All right, here we go. We are now going to be taking a look at some example problems on how to do orbital notation. You have a PDF file with these on there, so if you want to open this, you can do these right along with me on your PDF. Here's our first one. They're asking us to do an orbital notation for aluminum. Well, when you do an orbital notation, you have to find that element on the periodic table of elements. In your class information section on Google Classroom, we have a periodic table of elements. And we're looking for aluminum on here. Here's aluminum right here. And the reason we need to find aluminum on the periodic table is we need to know how many protons aluminum starts with. This is aluminum. Atomic number is 13, so aluminum starts with 13 protons. It says we are doing aluminum, not the aluminum ion. So we know that if there's 13 positives, there's also 13 negatives. 13 positive protons in the nucleus can only be neutral if there's 13 electrons. So we have to place 13 electrons, starting with the lowest energy level first. Aufbau says begin with the lowest energy sublevel combination. That's the 1s. So we're going to take the electron from the here. We're going to take an electron and we're going to move it into the 1s. There's our first electron for our orbital notation. Now we're going to move a second one, because we need to fill that sublevel first before we move on to the second level. Now, why can't I put another electron right like this? Why can't two electrons in the same orbital both have a clockwise or positive 1/2 spin? It would be breaking the Pauli exclusion principle, which says two electrons in the same orbital must have opposite spins. So we've got to get rid of that electron, and instead we need to put this electron in here spinning down. So I have a plus 1/2 spin going up, and the minus 1/2 spin is now going down. So I need 13. I've got 2 in there, so I'm down to 11 electrons, and now we are ready to move on to our next energy level. And we'll start filling the 2s first because it has lower energy than the 2p. The energy of the 2s was 2. The energy of the 2p is 3. Because when you're in the p sublevel, the second number is a 1. 2 plus 1 is 3. When you're in the 2s, the s, your second number is a 0. 2 plus 0 is 2. This is lower energy. Once again, these numbers above the boxes are the third quantum number, the m sub l. So there goes one in there. Now I need to fill this one before I move on to the next energy level. So now the 2s, or next sublevel. So the 2s is full. Now we can begin filling the 2p. I've got 4 electrons placed out of the 13. I have 9 to go. So here goes my next one, is here. What if I put my next one down? My next arrow, I decide I'm going to put down. I should not do that. What rule did I just break? I just broke Hund's rule. The second part of Hund's rule says when we have single electrons in orbitals, they must spin the same way. This is spinning this way. It will make this electron flip and spin the same way. So we've got to go all the electrons up, or we will be breaking the second part of Hund's rule. Here we go. I'm going to put another electron in. This one I'm putting right here. I am not allowed to do that. I have just broken the first part of Hund's rule, which says every orbital will have 1 electron in them before we begin pairing them up. This is a negative electron. This is a negative electron. So they'll push this one into the open orbital. And since these are both spinning up, it's going to make this electron also flip so that it would be spinning up. We're just kind of going over the different rules. There we go. Now, I've got 3 electrons in there. What am I doing wrong if I put the next electron over here? There I'm breaking Aufbau's order of filling, which says you must fill the lower energy level sublevel combination first. The energy of the 2p is 3. 2 plus 1 is 3. The energy of the 3s is also 3, because when you're in the s, your second number is a 0. 3 plus 0 is also 3. But why do I have to fill the 2p first? What is the tiebreaker when we have two different energy level, sub-level combinations with the same energy? Tiebreaker is the first number. So this electron can't go there until that entire sublevel is full. So here we go. We are now going to fill this sublevel. One there, and one there. We've now filled this one. If I'm not mistaken, we are up to 13 or 10 of the 13 electrons. So now I can advance. Now that that one's full, I can move up. Aufbau says I can build up to this next one. Here we go. One will go there, and one will go here. Now we have 2, 4, 6, 8, 10, 12. I need 13. So my final electron, by convention, we put the first arrow up. Now I have my 13 electrons. But we're not finished. I now need to put in how many electrons are in each of the boxes. This is the accounting part of it. This is just a way that I can quickly add up my total electrons that I've placed. You will be doing this on your homework as well. What I'm doing is typing as superscripts the number of electrons that are in that energy level, sublevel combination. The 3s, I'm sorry, has 2 in it, and the 3p only has 1 electron in the total in the 3 orbitals that it has. So 2 plus 2 plus 6 is 10, 12, 13. I've taken care of my 13 electrons. It's asking me for valence electrons in this box right here. Valence electrons are electrons in the outermost energy level. So I go through and I'm looking for my energy level number. That's the N. That's the first number that we see right here. My biggest number is a 3, but I also have a 3 here. So if my biggest number is a 3, I find where all the 3's are. There's a 3 here, a 3 here, and I'm going to add these electrons up. 2 here, 1 there. My total number of electrons is 3. So I'm just going to add 3 into this box right here, and I've taken care of that portion of saying how many valence electrons I have. Valence electrons, again, are electrons in the outermost energy level. Now it's asking me to look up the Roman numeral. What's the Roman numeral? That is the Roman numerals, the numbers that were written above the different columns or groups on the periodic table. And that was on our periodic table of ions. So I've got to go find the periodic table of ions. So I'm looking at the periodic table of ions. There's aluminum. I'm going up above aluminum, and I see right here that there's a Roman numeral 3 above the aluminum. So there's the Roman numeral 3 in the box. Is it a coincidence that the number of valence electrons is 3 and the Roman numeral is a 3? I don't know. You'll soon find out. Our next one they're asking us to do on our example problem is manganese. Manganese, I would look on the periodic table. I would look on my periodic table to find manganese. Here's manganese right here, Mn, atomic number 25. So I'm going to be doing manganese. Atomic number 25, that means it has 25 protons, so it should start with 25 electrons. So let's begin placing electrons. I start filling according to Aufbau, the lowest level first. I'm going to put 2 in the 1s. It's full. Aufbau now says move on to the next level. I'm going to put 1 there. And I'm going to fill the 2s before I proceed to the 2p. Once again, following Aufbau's order of filling. Once the 2s is full, I can now move on to the 2p. I'm going to follow Hund's rule and put 1 in each of the orbitals first before I double them up. I'm also going to follow Hund's rule by making sure that all the arrows are going the same way, indicating the electrons have the same spin. Now, Hund's rule will allow me to pair them up. By having one arrow up and one arrow down, I am following the Pauli exclusion principle, which says no two electrons in the atom can have the same set of quantum numbers. So now the 2p is full. And now I can move on to the 3s. Again, I need to keep going until I have 25 electrons placed. I have to fill the 3s before I begin filling the 3p, according to Aufbau. Now I can begin filling the next higher energy. Here we go. Once each of them get one before I begin pairing them up. Hund's rule. All the arrows are up before I start an arrow down. Second part of Hund's rule. So how many are we up to now? It's sometimes good to kind of keep track as you're going so you don't. We're looking for 25 total. I know I've got 2 in this one. I've got 2 in this one. In the p sublevel made up of 3 orbitals, I've got them all filled for 6. In this s sublevel made up of 1 orbital, I've got 2. In this p orbital, again, made up of 3 orbitals holding 6, it is full as well. So how many have I filled up so far? 18. I have 7 more electrons to place before I get a total of 25. So now I move to the 4s. You're like, but wait a minute, the third level also has a d. I realize that. But the energy of the 3D, when you're in the D, your second number is a 2. 3 plus 2 is 5. When you're in the S, your second number is a 0. 4 plus 0 is 4. So this one gets filled first. There we go. It looks like I now have 20. I need 5 remaining. So I will now begin to start filling up the 3D. There's 1. There's 2. Exciting stuff. Here comes 3, 4, and we are now finished filling up the number of electrons that we need. Remember, we've got to put our superscript in here to keep accounting of how many we have. There's 2 in that one, and I have 5 in this one. So that should be 25. 2, 2, 10, 12. 12 and 6 is 18, and 2 is 20, 25. This is manganese right here. They want to know how many valence electrons there are. Remember, valence electrons are the electrons found in the sublevels that have the largest number. So I start looking across my first numbers. The N is the first number. N is in orange. All the first numbers are in orange. My biggest first number is a 4. My biggest first number is a 4. This is a 3, so these are not valence electrons. This is the 4. Those 2 are valence electrons. So I'll come over to my box right here, and I'll put in the number 2. There are 2 valence electrons here. There we go. Notice they didn't ask us what this one asked for Roman numeral. This one didn't ask for Roman numerals. Wonder why that is? Well, for right now, if we're looking at the periodic table of ions, there are no Roman numerals above these right now. So they didn't ask for them because the periodic table that we were given here does not have those. We'll talk later on this year in one upcoming units why that is and what the Roman numerals are and what they mean. We will stop here after doing these first 2 example problems, and we'll continue on in the next video when we get an opportunity to do ions. Right now we've just done neutral atoms. We're now going to move on and do ions.